Good afternoon, AP Stats kids. It's Thursday, April 16th. Welcome back. I hope you were with Luke yesterday. Bivariate data, I think, least squares regression line. We'll take a look at his homework. I'm going to do planning a study and experimental design today. That's the goal, and I got some really fun free response questions that we're going to go through. So thanks for checking in. Thanks for watching again, and I hope you're safe. I hope you're healthy at home. We actually have our April break coming up next week. That's kind of a New England thing. So if you're not from New England, you might say, you know, why do you have an April break? But it's Patriots Day next Monday, and that's a pretty big holiday in New England. It's when they run the Boston Marathon, which is sort of a fun day if you're ever in Boston, if you're going to school in Boston. Unfortunately, this year, obviously, there's no Boston Marathon. But anyway, I hope you're safe. I hope you're at home. And thanks for watching, and we'll get started. So there's my intro slide as always. And again, my name's Brendan Murphy. I teach at John Baptist Memorial High School. You're probably getting sick of the slide if you've watched many of our videos, right? And Luke Wilcox, he's wonderful. He's a good friend of mine. We worked together many times, spoken together at conferences. I really enjoy Luke, and I actually watch most of his videos myself because I can always learn something from him. He teaches at East Kentwood High School in Michigan. Here's the homework from last night. So I don't know if you were watching. If not, no big deal. A scatter plot of student height in inches versus corresponding arm span length in inches is shown below. So bivariate data, my x-axis is my explanatory variable, my y-axis is my response. And so I actually do this. Sometimes I do height versus weight, or height versus shoe size, or height versus arm span. And we usually have a good discussion, you know. Why is height the explanatory variable and arm span the response? And honestly, this one probably could go either way. I don't know. You could probably talk to a medical professional. I'm going to say on an AP exam, if we ever asked a question about it, it would probably be pretty obvious what was the explanatory variable versus what was the response variable. So in this problem, we'll assume that the height is the explanatory and the arm span is the response. One of the points in the graph is labeled A. So A is over here, kind of on the right-hand side. If the point labeled A is removed, which of the following statements would be true? I'm just going to go to my problem here. Okay, if the point labeled A is removed, which of the following statements would be true? So let's say A, let's keep A in for now. I'm just going to eyeball sort of the least squares regression line. That's all it is. Okay, the calculator would do a better job, but I'm just trying to eyeball what I think that the least squares regression line would look like. And typically we want above half the points above and about half below. So again, a really bad eyeball. If the point A is removed, so if I take this away, well, then that line that I just drew doesn't represent the data very well, and so I'll kind of draw here in another color what I think that the new least squares regression line would be, again, if I moved point A. So here's the original, and here's without point. I have the cursor of a lefty, so you can't see what I'm doing, and I'm a slob. So it looks clearly like the slope is steeper, and my correlation coefficient R value would be stronger of the line. So the slope of the least squares regression line is unchanged. That's not a true statement. The slope of the least squares regression line is unchanged. That's not a true statement. The slope of the least squares regression line increases. Yeah, that feels like it did increase. The slope did increase. And the correlation coefficient increases. I think that's a true statement, and C is the correct answer. Just because statistics is sort of a gray, a branch of mathematics, or just a gray topic area, shades of gray. I like to typically read through the others just to make sure that I've answered it correctly. So let's just keep going. I think C is the correct answer here. The slope of the least square regression line increases. Well, that's a true statement, and the correlation coefficient decreases. No, that's not a true statement. The slope of the least squares regression line decreases. That's not true. So I'm pretty convinced that C is the correct answer. And again, that's just a test taking strategy. And of course, this year, there is no multiple choice, so we're not going to. Luke and I will not spend time reviewing that, but just in the future. To me, it's always just a good strategy to read through all of them, and sometimes reading another answer, something kicks out in my brain that I want to understand the problem a little bit better. Again, this is a typical slide. You've seen it before. This is all the updates about what you can do on the AP exam. Can you use your textbook? All that stuff. Down the bottom here is the schedule for Luke and I's remaining week and a half, 2 weeks, I guess 2.5 weeks. So you can always go back and look at that. I'll just keep moving and try and get into some math. So you've heard this probably thousands of times. Correlation does not prove causation. And I'm sure Luke mentioned it yesterday. He talked about correlation between two variables. And up until this point in the course, starting at, let's say, chapter 1 up to chapter whatever this is in your book, we've analyzed data numerically, graphically. We really haven't worried about where the data came from or how I collected it or how I got my data. And we haven't been able to say this causes that. And we do want to get there. We want to get to the point where we say this new medicine causes you to get better quicker. This new toothpaste works better than the old toothpaste or something like that. And so to do that, we need to get into what we call a well-designed experiment. And to me, it's one of the really fun units when I teach this to my students. I enjoy this. It's not mathy. I'm not going to use the calculator today. I don't even have that up on my computer because I'm not going to use the calculator today. Many teachers I know teach this sort of, chapter 4 in their textbook or whatever. Other teachers teach this day one. So I'm not sure, how exactly your teacher presented it to you. Either way is perfectly fine. I've done it both ways, and there's benefits to both. So this could have been the first thing you learned last August or September, or it could have been something that you were doing in December. But anyway, correlation does not prove causation. I'll try and build upon that today. We have 4 different ways in this course where we can how we can randomly select our data, I guess, so random sampling and data collection. We can have a simple random sample, SRS. That's an okay abbreviation on the AP exam. We know what that means. We try to discourage too many abbreviations. Please don't use text speak. We want you to communicate clearly using good statistical language, but SRS is perfectly fine. Stratified random sample is another way to randomize and collect our data. Cluster sampling is a third method. And systematic random sampling is the 4th method. That's newer to the curriculum. And so hopefully your teacher mentioned that to you. If not, maybe just make a note and go back and look at it. It's not complicated. It's a very easy way to collect data randomly. But it's newer to the curriculum. And so if you have an older book, it may not be in there. So just want to make sure that you understand that those 4 methods, we expect students to know the difference and how to correctly use them in a problem. I like to say to my students, each method has its strengths and weaknesses, no different than most things in life. So there are times when the simple random sample is the easiest and the best, and we want to use that. There's other times when the cluster sampling is really the best way, and it really topic specific, problem specific. So. And then here's sort of what the components of a well-designed experiment. And again, hopefully you've seen these before, but in A, we want comparisons of at least 2 treatment groups, one of which could be a control group. So I like to, summarize that as we need to impose a treatment. We don't always need a control group in every experiment we run. And that's where sometimes my students will struggle. They'll look at control group, and then we'll get down to D. And so I'll try and see if I can work that into one of the examples I do. We do not need a control group in every single experiment that we run, but we do need to control for variables. How's that? We need random assignment, allocation of treatments to experimental units. I'd love to be able to randomly select my whatever in my experiment and then randomly assign. Many times that's impossible, especially with humans and medical studies, but we need some randomization, and we need random assignment of the treatments to the different experimental units. We need replication, more than one experimental unit in each treatment group. More replication is typically always better. But there are times in the real world where if I was testing fertilizer on an acre of field, it might not be financially feasible to test thousands of acres. So we need more than one. Two is okay. Obviously, more is better. But given the constraints of the real world and things cost money, sometimes we're limited as to how much replication we can have. And then down here in D, we need to control of potential confounding variables where appropriate. I have a problem where we'll talk about confounding variables a little bit more. So, in summaries, we need to impose a treatment, we need some randomization, we need replication, and we need to control for outside confounding variables. So those are kind of the four components of a well-designed experiment. And as we walk through problems today, I'll try and just repeat those four. Do we have this? Do we have that? I have many students who take AP Biology or AP Chemistry or AP Physics, concurrently with AP Statistics. And I have had students say, Mr. Murphy, we do it a little bit differently in AP Bio. That's perfectly fine. I don't claim to be an expert in experimental design. I just say to my students, whatever class you're in, please follow the rules of that class. And when we actually get into a good discussion about how they do it in AP Bio versus AP Stats or some other class, it's really basically the same thing. But there are some subtle nuances there. And I won't claim to be an expert. If your AP Bio teacher says, do it this way, please listen to him or her. I'll defer to the experts on that. So we're going to take a look at some free response questions today. Try and get through as many as we can. So this is from the 1999 exam, AP Stats free response question number 3. And as an AP reader, some of these problems sort of take on lives of their own. And you hear readers talk about, the dentist problem in the boots. And so they each kind of get a name. And so this was the dentist and the apple problem. So a longtime reader will say, oh yeah, I remember that from years ago. So the dentist in a dental clinic would like to determine if there is a difference between the number of new cavities in people who eat an apple a day and in people who eat less than an apple a week. Again, just setting the stage, that's all. So is there a difference in the number of cavities based upon the number of apples you eat? That's all I get out of first sentence. They're going to conduct a study with 50 people in each group. Okay, so it feels like 2 groups, 50 people. They have 100 people in total. Again, I would want more than that in a perfect world, but I can live with 100. That feels like my sample size is big enough. 50 clinic patients who report that they routinely eat an apple a day, and 50 clinic patients who report that they eat less than an apple a week will be identified. Okay, so there's my 100 people. The dentist will examine the patients and their records to determine the number of new cavities the patients have had over the last 2 years. So at first I was thinking maybe this is an experiment, and now I'm leaning more towards an observational study. It feels like we've identified some people and the dentists have just looked at their records and made some notes or something. They will then compare the number of new cavities in the 2 groups. Going to switch over to my overhead. We'll take a look at the same problem. Okay, question A. Why is this an observational study and not an experiment? So maybe my gut feel there was right on. And I like this problem for many reasons, but I always say to my students, the College Board is telling you that this is not an experiment. So it would be pretty much impossible for you to get credit in Part A if you tried to tell us it was an experiment. So we're not trying to trick you. When we say something like, why is this an observational study and not an experiment? Please just believe us, and it is an observational study and not an experiment, and don't try and read into the problem. Sometimes my kids feel like, they really want to read into it or something like that. We're telling you that this is an observational study and not an experiment. So this is an observational study and not an experiment because the patient's dental records were just observed and recorded. So one sentence, I did try and get, patients or dentists and cavities, some context in there, which is super important. Down here in parentheses, I kind of came up with some potential other ways to correctly answer this. So in many ways, there's probably, you know, hundreds and hundreds of different sentences or sentence that you could come up with that would correctly answer this question. You could say this is an observational study and not an experiment because there was no random assignment of subjects to treatment. So again, we, you know, what do we have? We talked about, you know, imposing a treatment. We talked about randomization, replication, controlling for outside variables. We don't have any randomization here, therefore it cannot be an experiment. You could also say this is an observational study and not an experiment because no treatments were imposed on the 100 dental patients or something like that. So this is clearly an observational study. This is not an experiment. And there are many ways to correctly answer that. You don't need to list all of those. So don't worry about, you know, having to make a list of all the different things. You know, typically one way to answer it is perfectly fine. Okay, in part B, explain the concept of confounding in the context of this study. So sometimes I put a little 1 here. That's the first part of this question. Include an example of a possible confounding variable. Well, this has 2 parts to it, and we really need to make sure that we're answering both of those. And having read many AP Stats answers over the years, it feels like many students, unfortunately, will answer one of the 2, but not both, and maybe they don't realize there's sort of 2 different questions here, or 2 different things we're looking for. So if you're reading a question and it feels like there's more than one part, you know, make a little note, 1 and 2, however you want to do that. I'll leave that up to you guys. But that seems to help my students, and I want to make sure that we sort of have 2 different things here. So 2 variables are confounded if their effect on the number of new cavities cannot be distinguished from one another. In other words, I don't know what caused the cavities. That's one way to phrase it. Or confounding variable is one that was related to the explanatory variable and possibly influences the response variable. So again, I sort of came up with 2 somewhat generic definitions of a confounding variable. Both of those are fine. There's probably lots of other ways where you can also correctly identify it. But some of these definitional type questions are hard for my students. And they say, you know, Mr. Murphy, you seem to be able to just rattle this right off, but we're newer to this. And I always tell them, if you forget sort of the statistical language, just say it in plain old English, okay? And you'll probably be okay on the problem. So if you forget the exact phraseology or the words, just say it in plain English. You'll probably be okay. So don't worry about that. We're not looking for this exact language. How's that? Well, that feels like it's the first half, but not the second half. So include an example. So I need 1 example. Okay, there's many different rules at the reading. When we ask for 1 example, we want 1 example. If students give us 5 different examples, we actually read all 5 and we pick their worst answer. That may not seem fair, but we actually pick their worst answer. So when we ask for 1 example, give us 1. Mean it, be committed to it, define it well. But don't make a whole list and sort of say, well, you know, leave it up to the reader. They'll pick the right one. Well, we don't. We have to read them all. We have to read everything on your paper. But we're gonna unfortunately pick not the best answer and grade that one. So one example of a possible confounding variable could be the number of times a day that patients brush his or her teeth. That seems to me to be another factor in the number of cavities that you might get. Eating the number of apples you eat, I don't know if that impacts it or not, but I'm pretty convinced that every time I go to the dentist, he makes sure that I'm brushing 3 or 4 times a day. So and again, there's probably hundreds of different examples that could work here. And the readers are, you know, we're well trained before we actually read a paper. And so if you have a different potential confounding variable here than mine, don't worry about it. There's probably hundreds of different potential confounding variables, all of which could get you full credit. Okay, back to part C. If the mean number of new cavities for those who ate an apple a day was statistically significantly smaller than the mean number of new cavities for those who ate less than an apple a week. So there's a huge difference, how's that in plain English, between the two groups. Could one conclude that the lower number of new cavities can be attributed to eating an apple a day? Caused here might be another word, attributed. Sometimes my students get a little tripped up with that. Could be attributed to eating an apple a day, caused by eating an apple a day, explain. Well, to talk about causation, this caused that, we need to run an experiment. And in part A, we were told this is not an experiment. So my answer for part C is one cannot conclude that the lower number of new cavities can be attributed to eating an apple a day, because this was an observational study where you cannot draw cause and effect conclusions. So I many times just repeat the question, and I want to make sure that I get context in every part A, B, and C, you know, apples, cavities, dental clinics, something that relates to this problem. So I really like this problem. I do this every year with my students. And there's many sort of things that I'm trying to point out to them along the way. So this is the waterproofing in the boots. I'll cover up my answer here. This is from the 2002 exam. So this is the waterproofing in the boots. Again, this is sort of AP reader lingo, some of the old timers who've been reading for a while. A manufacturer of boots plans to conduct an experiment. So that's a key word. I'm going to underline that. To compare a new method of waterproofing to the current method. Okay, so I want to see if I can compare the old waterproofing to the new waterproofing. The appearance of the boot is not changed by either method. Super important sentence. Many times when I give this to my students, they sort of overlook that. When we talk about the best answer, someone will always yell out, "Oh, that's Mr. Murphy, why that second sentence was there." So I'll come back to that and I'll address that. The company recruits 100 volunteers in Seattle, where it rains frequently, to wear the boots as they normally would for 6 months. So that's just setting the stage. If we're testing waterproofing, I guess we want people to go out and jump in the puddles and see if the waterproofing works. And it does rain a lot in Seattle. Rains a lot in Maine, snows a lot in Maine. So you could do that experiment lots of places. But again, students may not know exactly how much rain happens in Seattle, so we're just setting the stage there. At the end of the 6 months, the boots will be returned to the company to be evaluated for water damage. Okay, so it feels like we have 100 volunteers. We're going to give them some boots. There are going to be different waterproofings on them, old waterproofing, new waterproofing. We want them to go out and wear them. We want them to go out every day, wear them in the rain. If they're a fisherman, we want them to wear them every day. If they're a high school math teacher, we want them to wear the boots when it's raining in school. And then after 6 months, they come back and the company is going to evaluate. And I think we're trying to determine here, you know, is the new waterproofing better than the old waterproofing? If it is, then they're going to make you know, the new waterproofing and put it on the boots. If not, they're going to stick with the old design. So describe a design for this experiment that uses the 100 volunteers. Include a few sentences on how it would be implemented. So I'm going to come up with a good design. I don't think it's the best, and I'll tell you why I'm coming up with it. While I'm kind of just working on it here, see if you can think of, you know, could there be a better design? So we always want the best design. So I call this an experimental design tree. I'm sure you know your books do this. And so, you know, here's my 100 volunteers. You know, and usually my kids put a big R here, and I guess that means randomize. And here's my old waterproofing up here, and here's my new waterproofing. You know, and they wear them for 6 months. They wear them for 6 months, and they come back, and you know, they evaluate the boots, record any damage, leaks, those types of things. So I call this an experimental design tree. I don't know if it has a more formal name, but hopefully you've seen this before. Hopefully, you know, the textbooks all have this. The reason I wanted to do this problem this way at first, even though there's a better design, is right now, this picture here is really worth nothing for credit on the AP exam. We think this is a good way to get your thoughts in order. We think this is a good way to set up the problem. But this picture here really isn't worth anything right now. I don't know what this R means. I mean, I think it means random, right? But I don't really know. So I encourage my students to come up with these, again, experimental design trees. I don't know if there's a better name, but we need below in a sentence or two or three really what you've just done. So I might say something like, I took the 100 volunteers and I randomly placed them into the two groups. And this is how I randomize. Usually just saying I randomly put them into the two groups isn't enough. We want you to actually tell us how you randomized. You could use a random digit table. You could use some sort of a calculator to randomize. I like to put the names in a hat, shake them up and pick them out. But we want you to just not put the word R or the letter R. So 50 people got the old waterproofing, 50 people got the boots with the new waterproofing. They wore them for 6 months. They came back and evaluated. So again, I wanted to do this picture here. Unfortunately, that's not worth any credit on the AP exam by itself. Down here, we want a couple of sentences explaining what you did. Sometimes if the communication in sentences down here isn't quite so strong, but you have a really good picture, as a reader, I can kind of look at both and try and figure out your answer. There are other students who have no picture here. They just say it in words and they do a great job, and that's perfectly fine. So I encourage my students to draw this type of picture here. It does seem to help them get their thoughts in order. And it feels like when we grade exams, if we have a good picture here, the sentences down here tend to be better. Okay, so that's a good design. But unfortunately, it's not the best design. So I came up with what I called a match pairs. So I said match pairs is the best design. Each of the 100 volunteers will be randomly assigned to either group 1 or 2 by picking a number from a hat. That was my first attempt. And I actually, this morning, when I went back and tried to do it again, said, you know, I think I need some more information. So I said, I'm going to put 50 number 1s in a hat, 50 number 2s in a hat, shake it up, and then ask each volunteer to pick a number. So I started out with my answer and actually read it the second time, and I said, you know what, I think I need some more detail there, Mr. Murphy. So that's another strategy. When you finally come up with your answer, before you submit it or before you turn it in, just read it again and see if you've addressed everything that you want. So in group 1, I said the left boot was old waterproofing, and the right boot was new waterproofing. So there's your match pairs. Each of the 100 volunteers is going to leave with 2 boots. One of them is going to be the new waterproofing, and one of them is going to be the old waterproofing. Group 2 is the opposite. Left boot, new waterproofing, right boot, old waterproofing. So that's a better design than this picture here. And if you came up with that while I was working, great. It's what we call kind of a classic match pair. Each volunteer will wear his or her boots for 6 months, and upon return, the boot evaluator, that's such a strange way to define that person, but I didn't know what else to call them. The boot evaluator will record damage, test for waterproofing leakage, etc., tears in the boots, and document their findings. So that's why this second sentence is just so important. And once I show my students this, and almost all of them kind of come up with this design here, and they get mad at me when I tell them it's not the best design. And then we talk about match pairs, and then they actually say, yeah, you're right, Mr. Murphy, that is a better design. So each person leaves with each of the different waterproofings. Here's my randomization. Some people get left old, right new. Some people get left new, right old. And that's important because and I've done this a million times in my life, every time I get out of the car, my left foot is the first one that hits the ground. That's just probably all of us are that way, right? When we get out of the car, your left foot is the first one out. And I've put my left foot in many a different puddle and said, well, this was probably a stupid place to park, Mr. Murphy. Maybe I should have backed up another foot or 2. So there's my randomization. That's good. Each person leaves with the old and new waterproofing, and it's just a better, stronger design. Part B, could your design be double blind? Explain. So double blinding, if possible, is typically always better. So we do want to double blind this experiment if we can. There's probably some experiments in the world where we can't, but I'm going to say in AP Stats that I tell my students, we pretty much think about double blinding if at all humanly possible in all the different experiments. So I think we can double blind here. So I said, yes, my design could be double blind as long as the 100 volunteers and the boot evaluator, again, that's such a strange term, isn't it? The boot evaluator, do not know which boots were treated with which waterproofing new or old. So if I'm a volunteer, I go in, someone gives me a size 13 pair of boots, and I'm happy because I got a free pair of boots, and I go wear them for 6 months. So I don't know which boot got which waterproofing. I don't really care. I got a free pair of boots, and I'm good to go. The boot evaluator, the person who actually gives me the boots, when I return them 6 months later, does some sort of testing, they don't know. And so therefore it is double blind. What my students get confused sometimes is, well, who knows what's going on then, Mr. Murphy? Like who really knows? And I like to say, well, there's a third person. There's the person in charge of the experiment. There's the person who's in charge of waterproofing for the company. So there's a third person who knows exactly what each one of those 100 volunteers got. I, as a volunteer, don't know. I shouldn't know. I don't really care. I got a free pair of boots. And the boot evaluator, as soon as I come in after 6 months, they're just going to test the boots. And it's actually better that they don't know, because they could enter some bias into it and say, oh, you know, Mr. Murphy, I can't believe the left boot is actually better than the right boot, or something like that, if they knew which one was the old waterproofing and which one was the new. So it can be double blind. It should be double blind, and it's just a much better experiment that way. So I love the boots. It's sort of a classic, and I always have fun with that with my kids. And they say, you come up with the strangest examples, Mr. Murphy. You have a very creative mind when I talk about my left foot going out first. So I think this one is going to get into maybe stratified versus cluster sampling. Again, these were two of the randomization techniques that we want students to know how to use. We probably won't ever get a definition. We probably won't say, define the following word, but we do want you to use it contextually in a problem. And so there is a difference, and we'll talk about which one was probably better here. So this is from the 2011 exam. An apartment building has 9 floors, and each floor has 4 apartments. That's what we're trying to show you here. First time I did this problem, I actually had to spend a minute trying to figure that out. It took me a little while. It was a little slow, but I figured it out after a while, and there's my 9 floors, and each floor has 4 apartments. So I guess there's 36 apartments in total. Couldn't figure out what the asterisk meant. Of course, I just needed to read, right? So if it has a little asterisk, there are children in the apartment. So apartment number 11, I guess, has children. 22 does. None on this floor, none on that floor, etc. So understand the problem before you go and actually start to answer any questions. And I think that it's well worth the extra minute or two up here understanding the problem before you actually start to answer the question. So I tell my students, if you need to spend another minute, go back and read it, underline keywords, whatever, perfectly fine. The building owner wants to install new carpeting in 8 apartments to see how well it wears before she decides whether to replace the carpet in the entire building. Okay, that makes sense. Before the landlord does 9 floors of carpeting, they want to sort of test it out, see if the new carpeting works well. And so they're gonna pick 8 apartments, I guess, 2 floors, and try and figure out whether the new carpet's worth buying, and that makes sense. The figure below shows the floors of apartments in the buildings with their apartment numbers, so apartment 11, 12, 13, etc. Only the 9 apartments indicated with an asterisk have children in the apartment. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. I missed one maybe there. 9 apartments. Okay, why is that important? Again, probably somewhere in the problem, they're going to talk about the difference between children in the apartments, but my gut says the children are running around and probably having a good time and perhaps spilling stuff. And my little nieces and nephews, I love them to tears, but sometimes they can run around and make a mess. And that's just sort of the way it is, and I love them for it. Okay, in part A, for convenience, so I'm going to circle that word. Sometimes doing the easy way isn't the best way. For convenience, the apartment building owner wants to use a cluster sampling method in which the floors are clusters. So I guess that would be a cluster, that would be a cluster, that would be a cluster, et cetera, et cetera. So looking at it quickly, it looks like I have 9 clusters, right? For the 9 different floors. Describe a process for randomly selecting 8 different apartments using this method. Okay, so I have 9 different floors, and it feels like I want to randomly select 2 different floors. And then what cluster sampling says, well, then I'm going to sample everything on that floor. And so there would be 4 apartments and 4 apartments. So before I even go to write anything, I just want to understand what's going on. I have 9 floors. Each one I'll call a cluster. I want to randomly select, I guess, 2 floors. And then I'm going to put new carpeting in all 4 apartments on those 2 floors for a total of 8 apartments. And that's what the landlord wanted to do. Okay, again, there's different ways to randomize. You can use a random digit table. You can use some sort of a calculator or a random number generator. I'm sort of a big fan of putting the names in a hat or the numbers in a hat, and that's what I tried to do here. So I said, put the numbers 1 through 9. Each number corresponds to the floor in the apartment. So number 1 is floor 1, number 2 is floor 2, et cetera, et cetera. In a hat, shake it up. That's actually important. So if you use the hat method, we need to shake it up, and that's important. And pick out 2 numbers. So I'm going to put numbers 1 through 9 in a hat. I'm going to shake it up, and I'm going to pick out 2 numbers. Those 2 numbers would correspond to the 2 different floors. And then for each apartment on these 2 floors, so 2 floors times 4, there's my 8 apartments. These apartments would be selected for new carpeting. Okay? So that's one way to do it. I think I've answered the question, but I'm not really sure I like that method a whole lot. I circled the word convenience, and I said to myself, could I randomly pick the 6th floor and the 4th floor here? And the answer is yes, I could. The problem with that is it doesn't look like there's any children in any of those 8 apartments. And as a landlord, I probably understand that there could be, no guarantees, there could be different carpet wear or carpet usage if there's kids on the floor versus two adults or something, or 1 adult. So I think part B sort of addresses that. An alternate sampling method, so this was cluster sampling, would be to select a stratified random sample of 8 apartments, where the strata are apartments with children and apartments with no children. So stratified random sampling, I have different strata, different groups with similar characteristics. How's that? A stratified random sample of size 8 might include, so I still want my 8 apartments, right? Still want the 8. Might include 2 randomly selected apartments with children. So I want 2 with children. And 6 without children. And again, that's good. I want both, right? I want both. Hopefully they're somewhat proportional, right? In the context of this situation, give 1 statistical advantage. That's all I want to give. Maybe there's 3, maybe there's 5, maybe there's 10. I want to give 1. I want to commit to that. I want to be clear and concise in my answer, and I want it contextual. Give 1 statistical advantage of selecting such a stratified sample as opposed to a cluster sample of 8 apartments using the floors as clusters. So I think we already talked about it in part A, the convenience. I theoretically could have picked 2 floors randomly, nothing wrong with that. But if I had picked those 2 floors, or maybe if I had picked floors 3 and 6 or something like that, I wouldn't have any apartments with children, and that strikes me as not the best design. So 1 statistical advantage of this stratified sample is you would guarantee to get apartments with children and apartments without children, as opposed to the first design where we theoretically could have gotten 8 apartments with no children. So to me, that was the real benefit of the stratified random sampling there. It is reasonable to assume that wear on the carpets could be, I don't know if that's a fact or not, could be different for apartments with and without children. And if you have younger siblings at home, or maybe when you were a younger person, you ran around the apartment and had fun. So that's really just sort of testing, do you understand the difference between cluster sampling and a stratified random sample? And again, the benefits of those two different methods, or two different design techniques. So let's see if I can get into this last problem real quick. I'm watching the clock here in the corner here. I think I can at least start this and hopefully not go too fast, but hopefully I can put a good dent in this. So this was a more recent problem for the 2016 exam. Alzheimer's disease results in loss of cognitive ability beyond what is expected with typical aging. Terrible disease. I hope one of you go out and find a cure for Alzheimer's. How's that? Make the world a better place. A local newspaper published an article with the following headline. Study, I don't know what that means, observational study experiment, I don't know. Study finds strong association between smoking and Alzheimer's. Okay? Again, study, I don't really know what that means. Association, is this an experiment? Again, it's probably where the problem's going, but I'm just sort of thinking about the problem as I'm reading it. An article reported that a study tracked the medical histories of 21,123 men and women for 23 years. Okay, that's a pretty long time, so that's good. That's a pretty good sample size, that's good. But tracked the history sort of feels like an observational study to me. It doesn't really feel like an experiment to me. But let's keep going. I'm just thinking about the problem as I'm reading it. The article stated, for those who smoked at least 2 packs of cigarettes a day, the risk of developing Alzheimer's disease was 2.57 times the risk for those who did not smoke. So if you were a smoker, you did, I guess, based upon this study, have a higher risk of getting Alzheimer's disease. But I don't know if we can talk about causation here. Remember earlier, one of my slides was correlation is not proof causation. Okay, identify the explanatory and response variables in the study. So the explanatory variable, the degree or the amount of cigarettes that a person smokes, or the number of packs a day a person smokes, or something like that. The response, whether or not a person develops Alzheimer's disease during the course of this study. So is the amount of cigarettes or number of packs of cigarettes that you smoke, is that helping to explain the whether you develop Alzheimer's disease or not? Is this study described in the article an observational study or an experiment? Explained. So again, experiment, I'm kind of thinking about 4 things, right? I need to impose a treatment. I need to have some randomization. I need replication. I need to control for outside variables, confounding variables. And I don't think we meet that here. I don't think we meet that at all. So this is an observational study and not an experiment, because smoking status amount was just observed, not manipulated by the researchers. So we just recorded what those 21,000 people did for 23 years, which is a pretty big sample size in a really long time frame. But we were not manipulating or controlling how much or how little they smoked. And obviously there's some real ethical issues with that. So this is not an experiment. Exercise status, regular weekly exercise versus no regular weekly exercise, was mentioned in the article as a possible confounding variable. So we talked about that. It's a good word to know, sort of definitional and how to use it. Explain how exercise status could be a confounding variable in the study. Okay, so it looks like perhaps those who exercised may impact the response, whether they got Alzheimer's or not, and maybe that's kind of clouding up whether it was related to smoking or not. Every time I go to my doctor, he asks me, "Are you exercising, Mr. Murphy?" So it feels like every doctor I go to asks me that. So exercise status, and those folks who exercise more, they might be more health conscious and less likely to smoke cigarettes than people who do not exercise. It is also possible that the people who exercise more are just less likely to develop Alzheimer's disease than people who do not exercise as much. And then I sort of added this again kind of down the bottom here, and this probably may not be needed, but again, I just wanted to, this was sort of a note to myself. A confounding variable is one that is related to the explanatory variable and possibly could influence the response. So the fact that you exercise or how much you exercise could kind of be related or somehow tied into how much or how little you smoke. I would assume that people who exercise all the time might not smoke at all or smoke less than people who don't exercise. So hopefully that helps a little bit with this experimental design. Planning a study. Those are 3 or 4 free response that I found and used over the year, and I tried to pick different problems for different things. I don't think we did this one, but this one is talking about convenience sampling and wording bias. So you might want to go back and, when you're looking at this slide again or looking at the webinar, maybe go back and take a look at this. This is from the 2004 exam. We did that one and we went through that one, hopefully not too fast, but hopefully I did at least a decent job with that. So hopefully by now you're feeling more comfortable with using the different random sampling techniques. Again, we talked about the 4 and designing an experiment to show causation. That's kind of the big word. I want to be able to, at the end of a well-designed experiment, say this caused that. Similar to every single problem probably that Luke and I do in AP statistics, probably just in life, you should be able to write a clear, concise solution in context. It's so important that every part of your problem, part A, part B, part C, whatever, you relate it specifically to that problem. We don't like these generic answers that you can use year after year after year after year. So here's your homework for tonight from the 2012 multiple choice. Luke will go over that tomorrow. I think it's related to experimental design. I think tomorrow he's doing FRQ Friday, so free response Friday. I did one a couple weeks ago. He's doing one tomorrow. So again, we know that all students we know that all students do not have access perhaps to the internet or device, and of course this year's AP Stats exam will be taken at home, most likely, or over some sort of a device, computer, laptop, phone. College Board's working on solutions to help students get what they need to show their best work. So if you're interested in taking the AP Stats exam, and we hope you all do, that if that's a problem, connectivity, or you don't have a device, please, please, please reach out to the College Board at the link below. Contact one of your teachers, your AP coordinator, your AP Stats teacher, someone, and the College Board will work with you to make sure that you can, we'll try and get you a device in hand. So that's it for today. I think I went over a few minutes. I hope I didn't keep you too long. I hope this helped. So thank you very much again for sitting in. You'll be with Luke tomorrow. I'll be back with you guys on Monday. So please be safe. Please stay positive, and keep working hard. And we hope that all of this work that Luke and I are doing is helping out, and we appreciate all the hard work that you and your teachers have done. So I'll sign off for today. I'll see you guys next Monday. Have fun with Luke tomorrow, and we'll see you on Monday.